So it's called the Josephus problem. It's based on something from history. There was a group of Jewish soldiers who were surrounded by the Roman army, and they didn't want to get captured, so they decided to come up with a system to avoid getting captured or suicide. So they'd sit in a circle, and the first man would kill the guy to the left of him. The next remaining living person would kill the next remaining living person with their sword, and they'd go around like this until there's only one person left, and then the last person would have to commit suicide, of course, rather than get captured. And the story, at least the story I was told, I'm not sure this is historically accurate, was that Josephus preferred capture to suicide, but he worried that if he said this, the other soldiers would turn on it. And so he wanted to figure out where should he sit within this circle in order to be the last man living, and then he would surrender rather than kill himself. That was the problem. It's a little tricky, so let's do a smaller example. Let's say there were 7 people. And so just to be clear, the way it works is person number 1 kills number 2. Person number 3 kills 4. 5 kills 6. But now things get a little harder to kind of see in advance, because 7, there is no 8, so 7 kills 1. 3 kills 5. 7 kills 3. So 7's the winner. 7's the last one left over. For Josephus, there were 41 people. He needed to figure out where to sit. The mathematical problem is if there were n people, where's the winning seat? When I learned this problem, I was in high school. And it was one of the first problems that got me to understand how you approach difficult and math problems where you don't know the answer in advance, where someone hasn't shown it to you in advance. And it was a professor of mine. His name was Phil Hanlon, who played a big role in kind of leading me to math. And he suggested what we should do is we should gather data. Just take various values of n and just do it by hand and start looking for a pattern. I don't know, maybe we should just do that. N is the number of seats, and W of n will be the winning seat. And so what we know so far is that n is 7, W of n, it turns out, is also 7. And so what I would do is I'd start doing some other values. So I don't know, why don't I do 5? So 1 kills 2, 3 kills 4, 5 kills 1, 3 kills 5. The winner is 3. I guess there was no reason for me to skip 6, so why don't we fill in 6? Kills 2, 3 kills 4, 5 kills 6, kills 3, 5 kills 1. The winner is 5. So if you're watching, you might already start to notice some patterns. For instance, they're always odd. I mean, that's maybe the first thing you notice. And you can start to ask yourself, well, why are they always odd? And maybe you can already see that, right? The first loop around, all the even people get killed. So you can even with just a tiny amount of experiments start to see some patterns.
So you don't want to sit in an even seat.
Don't sit in an even seat. No. And maybe we're even getting some glimmers of other patterns. But before I really try to phrase those, I'd like to fill in the table a little bit more. So let's do some. So if there's only one person, well, that person's the winner. So that one was easy. If there's 2 people, 1 kills 2, 1's the winner. If there's 3 people, 1 kills 2, 3 kills 1, 3's the winner. If there's 4 people, 1 kills 2, 3 kills 4, 1 kills 3. If there's 8 people, 1 kills 2, 3 kills 4, 5 kills 6, 7 kills 8. 1 kills 3, 5 kills 7, 1 kills 5, winner is 1. All right, so it was 1, 1, 3, 1, 3, 5, 7, 1, 3, 5, 7, 9. And you could keep going, but maybe you can see the pattern now.
I think it's 13 or 1.
No, good guess, actually, but it's not a 1. Brilliant. So let's do 13.
This is good. I don't know then. I can't see the pattern.
So as you see, it's jumping by 2 each time, but then it resets at some point. And I want to go back to this. So we'll see what 13 is quickly. Cool. So we didn't reset there. I claim we won't reset at the next one either. 14 will be 13. And here, by the way, we're starting to make predictions. It's worth noting even though we maybe can't say exactly what like 178 would be, we're starting to see the pattern well enough that we could make a prediction. So you could guess, is it really true that 14 is going to give you 13? And we could do it out, and you'll see, in fact, that's what you'll get. So we're getting some understanding. But I want to go back to this point you had. You asked if it was going to reset and go back to 1 there. And the answer was no. And it's worth looking, because this is the next thing I was going to do. Where do we get the 1s? So if you look for a sec, there's something very special about the numbers that give you 1s. It's the powers of 2. And so maybe you can now guess that if I put in a 16, I would get a 1 back. And that'll be right. And that's actually going to be a real key. in unlocking this. The professor I was learning this from made a really big point out of this. And I thought, well, I don't know what the general answer is yet. And he made a big point. If you know something, prove it and make sure you really understand that one thing. And that often unlocks the rest. So he really pushed us when I was first doing this to try to state a conjecture and then prove a theorem based on what we just saw here. And so that's what I want to do. So here's the conjecture, is that if n is a pure power of 2, then the winning seat is 1. I want to think about this for a second and maybe see why this might be true. So let's do the next biggest power of 2, maybe the biggest one I can bother writing down. So let's do 16. So I want to do one pass through the circle.
Take out all the evens.
Take out all the evens. And now 15 has just killed 16. So I'm going to put a little dot here so we remember it's number 1's turn again. And it's number 1's turn again, and we've removed all the evens, and what's left is therefore exactly half as many. So if I relabeled at this point, you can see that there was a power of 2 to start with. I pass through the circle once, I get rid of all the evens, I have half as many, and I'm back at number 1's turn. So now if I do this again, the same thing ought to happen, right? I should kill all the evens under the new labeling. And now there are 4 people left, and it's still number 1's turn. So you go through again, kill those guys. There's 2 people left. It's still number 1's turn. And now 1 kills that, and it's still number 1's turn, and that chair wins. So let's say we believe that. We know what happens for 2 to the n. So how do we explain what happens between the pure powers of 2? If you see the pattern, we know what happens at 8, and we know what happens at 4. But between them, it goes up by 2's until, at this point, if I added 2 to 7, I'd have a 9, which would be too big anyway. So that's our reset. But we knew it was going to reset because it's a pure power of 2. So how do we explain this jumping by 2 phenomena in between? And so what I'm going to do, I'm going to just mention that for any number, you can write it as a big power of 2 plus something else. Take the biggest power of 2 you can subtract from a number, and then what's left should be smaller than that. When you express a number in binary notation, you choose zeros or ones, and that gives it as a sum of a bunch of powers of 2, and you just choose the biggest one. So 77, the biggest power of 2 I can get is 64, and then what is it? It's 64 plus 13. So then for 13, the biggest power of 2 is 8 plus 4 plus 1. Did I do this right? 72, 77, there you go. And these are all powers of 2. And this is unique. This is the unique way to write 77 as a sum of powers of 2 where no power is repeated. That's a key point. So if you wanted to take a general number, take the biggest power of 2, 64, and then the remaining part, 12, 13. I'm going to call this part 2 to the a, and the remaining part I'm going to call L. And I claim that this L is going to tell us which of those odd numbers between is going to show up. So let's see how. How about we do 13? N is 13. This is the binary expansion, but using our new method, the 8 will be the 2 to the a, and the 5, which is the 4 plus 1, that'll be the L. And here's the thing that's going to happen with the L. I'm going to do 5 steps. So 1 kills 2, 3 kills 4, 5 kills 6, 7 kills 8, 9 kills 10. So now I've dropped L people, and it's number 11's turn. Now watch what happens. How many people are left? Well, what's left is a power of 2. And we know who wins in a power of 2. It's whoever starts.
The first killer.
The first killer. So now, if we go from here, I claim that 11's going to win. And just watch. It's going to be 11 kills 12, 13 kills 1, 3 kills 5, 7 kills 9. Back to 11, and now there's only 4 people left. 11 kills 13, 3 kills 7, back to 11, 2 people. 11 wins. And so this is really the key to the final answer, which is if you've written your number as 2 to the a plus L, after L steps, whoever turn it is going to win, because it's going to be their turn and there'll be a power of 2 left. And so the winning seat will be 2L plus 1 if you write it in this way, because that's whose turn it'll be after L steps. The theorem, or the claim, is that if you've written n in this way, so if n is 2 to the a plus L, where L is less than 2 to the a, it has to be strictly smaller. So in other words, 2 to the a is the biggest power that sat inside of n. Then the winning seat is going to be 2L plus 1. So we've already seen it was true here. right? L was 5, and the winning seat was 11, which is 2 times 5 plus 1. And if you start going back through, you'll see the same thing for all the answers. We've already really illustrated the mechanism, which is after L steps, it's the turn of person 2L plus 1. And after L steps, there are a power of 2 number of people left. And when there's a power of 2 people, the first person who kills, that's who's going to be the winner.
Let's see if Brady has learned.
Yeah, all right, let's do
try
it.
This. I think I followed. Now, in the Josephus problem,
Yep.
there was Josephus and 40 soldiers. So
That's right. Oh yeah, we got to go back and do that.
All right, so we've got 41 people.
So N is 41.
All right, so now, I think expressing that in the way you told me to, it's going to be 32 plus 9.
There you go. 32 plus 9.
So 2 lots of 9 plus 1 is 19.
There we go.
So we want to sit in position 19.
There you go. You want to sit in the 19th chair. So here we go. We're going to do N equals 41.
All right, put them in the cave, waiting their fate.
Not a very good circle,
That's
but
all right. Small them down.
I know. Should I redo this?
No, you're okay.
40, 41. Okay, there we are. So we got a little tight at the end.
Look
All
at
right.
that. This is a lesson about planning ahead, people.
Yeah. Okay, so let's do it. 1 kills 2, 5.
We're losing our even numbers.
Yep. Okay, now 41 kills 1. 3 kills 5. And 19 kills 35, and there we go.
All right, I was right.
There we go, 19.
Right.
I'll note one other thing in this problem, which is kind of fun. So this formula I wrote can be interpreted in binary notation. When we wrote a number as a sum of powers of 2, this can be re-expressed in binary notation. So what was this? 32 plus 8 plus 1. So that's 2 to the 5th plus 2 cubed plus 2 to the 0. And binary notation, the digits correspond to the various powers of 2, and all the digits are 0 or 1. So 41 in binary notation would be 1 copy of 2 to the 5th, 0 of 2 to the 4th, 1 of 2 to the 3rd, 0, 2 squared, 0, 2 to the 1st, 1 to the... Here's a trick for the Josephus problem, which I won't justify, but it's super cool, and you can try it on your own. The way to find the winning solution, if this is n, the winning solution in binary is you take the leading digit and you put it at the end. So in other words, I claim that if I write 0, 1, so I take this part and then I add the first digit to the end, that number in binary code is, well, let's see, it's 2 to the 0 plus 2 to the 1 plus, I skipped 2 squared and I skipped 2 cubed, and I add 2 to the 4th. So it's 2 to the 4th plus 2 to the 1 plus 2 to the 0, which is 16 plus 2 plus 1, which is 19, which is exactly what the winning seat was. And so there's this super efficient way in binary code to jump straight from the number n to the winning number w of n. So if you're writing your numbers in binary code, the pattern would have been even more quickly apparent. Isn't that cool?
Yeah.
Yeah. Isn't that cool?
Yeah. This video was filmed at the Mathematical Sciences Research Institute, MSRI. That's the building